Hey everyone, Brandon Quinn here, thanks for joining. In today's video, we're going to take a look at a logic puzzle from my book Mental Mosaics called Minutes and Hours. So the problem reads, on an analog clock, how many times a day do the minute hand and hour hand overlap? Now be warned, this problem isn't quite as simple as it might seem on first glance. Pause the video now if you want to try this problem for yourself, and when you're ready, come back and we'll review the answer. Typically, when people try to solve this logic puzzle, their first reaction is to blurt out that the answer is 24. But let's do a little bit of an experiment here and see what happens when the clock on the screen moves to 1 o'clock. Notice that the hands didn't intersect at all through that time period between 12:01 and 1 o'clock. They actually don't intersect again till slightly after 1:05. So if the first intersection is right at 12 o'clock on the dot, and the second one isn't until 5 minutes after 1 o'clock, then that means the interval between intersections is greater than an hour, which means that the total number of intersections must be less than 24 in a day. There's two ways we can solve this problem. We can work it out logically and find the exact number of intersections using deductive reasoning, or we can work it out mathematically and find the number of intersections by finding the exact interval of time between intersections. In this video, I'll go over both approaches, starting with the logical approach. Let's make a few observations about how the clock behaves with respect to the minute and hour hands, and see if we can draw any conclusions about the number of intersections in total. The first observation is that the first intersection happens directly at 12 o'clock on the dot. The second observation is that, as we discussed before, the next intersection doesn't happen until slightly after 1 o'clock, right, which means that the interval is slightly greater than 1 hour. Next, notice that the previous intersection, that is the one before the 12 o'clock intersection, doesn't happen at any point during the 11th hour, right, because the 11 o'clock position, the hour is pointing at 11, the minute is pointing at 12, and the next intersection after that is the one that happens directly at 12 o'clock on the dot. So there is no intersection during the 11th hour whatsoever. So what conclusions can we draw from those observations? Let's answer that by asking ourselves a question: are there any other hours throughout the day that also don't have an intersection? Like we discussed before, 11 o'clock does have an intersection, but let's think about the 10th hour. So on the 10th hour, the minute hand starts at the 0 and the hour hand starts at the 10. The 11th hour, the minute hand also starts at 0 and the hour hand starts at 11, which means there must have been an intersection of the minute and hour hands between 10 o'clock and 11 o'clock. Moving to the other side of the clock, right, let's think about the second hour. At 2 p.m., the minute hand is on the 0, the hour hand is on 2, and comparing it to 1 o'clock, the minute hand is on 0, the hour hand is on 1. So there must also be an intersection between 1 o'clock and 2 o'clock, and then we can use the same reasoning to show that there must be an intersection between 2 and 3, 3 and 4, 4 and 5, everything all the way up to 10 and 11. This means that every hour other than the 11th hour has an intersection. So if you rotate through the clock for 12 hours, you'll have 11 intersections. And since the question asks how many intersections are there in a day, we now know that there are 22 intersections total within a single day. Alright, with that, now let's try to solve the problem using the mathematical approach. We're going to take a similar approach to the logical approach in that we're going to make a few statements akin to observations, such as the number of minutes in a day, and then put them together to calculate the precise interval between intersections and then divide that into the total number of minutes to determine how many intersections occur within the day. So just multiplying out the minutes and hours, we see that there are 1,440 minutes per day. Now let's model the intersection time. Recall from before how we were saying the intersection is just a little bit longer than an hour. It's an hour plus the portion of time that it takes for the hour hand to catch up to the minute hand's additional progress. So we're going to phrase intersection time as t equals 60 plus x, where x represents that additional catch-up time beyond the hour. Next, we want to isolate x, and how can we do that? We can think about it by observing that at 1 o'clock, the minute hand is on the 0 and the hour hand is on the 5, so it's going to take a little bit of extra time to catch up to that hour hand. So 5 minutes later, the minute hand is now where the hour hand was, but in that time, the hour hand has advanced slightly, the same amount scaled down to 5 divided by 60, as in 5 minutes. So we can rewrite x by stating that x is equal to 5 plus 5x divided by 60. Sort of a self-referential or recursive definition there, but we can factor that out. Simplifying the equation, we can see that x is equal to 60 divided by 11, which is roughly 5.5 minutes. From there, we can calculate the total intersection time by adding that back into 60. So t is equal to 60 plus x, which means t is equal to 60 plus 60 divided by 11, which means t is equal to 720 divided by 11, or roughly an hour and 5.5 minutes. Lastly, we can divide that intersection time into 1440, the total number of minutes in a day, at which point we see that we got 22 intersections. So through two separate approaches, we were able to arrive at the correct answer of 22. In the past, when I've given this problem to people, I've noticed a certain reluctance to accept the correct answer of 22. So I've included here an animation that shows the intersections on a sped up clock as time moves throughout the day. The first intersection occurs at 12 o'clock on the dot. So this is one intersection, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Notice that we don't count the 12 o'clock again because that would be the second cycle through the clock. And also notice you have to multiply the 11 by 2 because there's 2 cycles throughout the day. By the way, that is one sort of funny way of solving this problem. Just grab a real analog clock, cycle through, and count the number of intersections. So we've solved this problem in 3 ways, really. 1, the logical approach, 2, the mathematical approach, and 3, the wind up the clock and see what happens approach. And in each case, we got a total of 22 intersections. I hope you've enjoyed this puzzle. If you did, I highly recommend you check out my puzzle books Mental Mosaics and Hexakai, where I have hundreds of puzzles on a wide array of topics and difficulty levels. Links to both books are in the description below. Thanks for watching, I'll see you next time.